Let me start. Today lecture, and these two lectures I will present you stochastic differential equations with interaction. The first lecture will be devoted to the general construction and properties of such equation, and the next lecture we will discuss the questions which we can investigate relatively to obtaining measurability processes and stochastic flows. So let's start from the sum motivation. Let me recall you some deterministic equations which are related to usual differential equations, but the aim of such equations is to present some much more complicated picture. The first example is a Helmholtz equation. He introduced this equation when we studied the flow of the liquid, and usually we believe that the flow of liquid or gas can be described by the Euler or later Navier-Stokes equation. But we know that such kind of equations are nonlinear partial differential equations, which in general case cannot be solved explicitly. Even it is hard to obtain theorem of existence and uniqueness of the solution. So it is desirable to find the model which can be much more easy investigated and reduced to ordinary differential equation. And Helmholtz proposed such model and it looks like follows. We substitute the flow of liquid by the motion of the small vortices. So we have a lot of small, infinitesimally small vortices. So a lot of such points, but this is not only point, it has vorticity. And now one can study the motion of all such systems by writing system of the differential equations for these vortices. And if we denote at the time t, denote the position of the vortice as in t, then in dimension 2, one can write the following equation for this coordinates. We will have the following equation. d r dt is equal to minus 1 over t. Some here we have the sum which is j, which is not equal to I, And the sum of the following kind. This is kj, and gradient. I will explain what is it. A gradient of the logarithm of the norm of the difference r it minus rj. Here the sign orthogonality near gradient means the following. We have the vector a, and we rotate it anti-clockwise. Here we get vector a. So we have such a system of equations, and of course it is not very simple because of such not good right part, but still it is simpler than initial Euler equation. And it occurs that such Helmholtz equations can be studied from the point of view of asymptotic behavior. One can try to find invariant manifolds and so on. What is important for us in this equation? Let us mention that this equation can be rewritten in the very interesting form. Let us define the following object. Mu will be mu t will be equal the sum of I equal 1 and this is the number of this is k I, and here is delta r I t. What is this? What does it mean? This value? This is a delta function at the point r I, and it can be understood as a measure which have unit mass and concentrated at this point. So when we consider this sum, after such definition, we understand that we have here a measure on the our plane. We remember that the dimension of the space is equal to 2. So we have such notation, and after this one can rewrite the right part of the equation as follows: d I t is equal minus 1 5 integral with respect to r2. Here we put this function logarithm r I t minus u, and then mu t d. Mu t d. Of course, when we write such an integral, we have to make some agreement about zero here. Suppose that we define this logarithm equal to 0 when we have 0. Okay, this gradient equal to 0. Okay, then we have such such an expression, and when we consider such expression, one can understand that this measure mu t can be obtained as an image of the initial measure under some mapping. To organize this mapping, let us enlarge this equation. You remember, this equation was written for points which are infinitesimal points. But let us try now to write this equation simultaneously for all points of our space. How one can modify it in this way? Let us write together with this equation the formula dx vt is equal minus 1 over pi integral up to, here is the same function, logarithm, x vt minus mu t, excuse me, mu t du dt. Let us consider the following equation. Here, the point xvt will start from the point v, and now v is arbitrary point of the our. One can see that if this v is equal to I from 0, then we get the same equation. So we enlarge our Helmholtz system to the family of equations, where we discuss the motion of any particles from the space, regardless is it equal to initial vortex or not. So we can transform our equation in this way, but still we have this mu t, which was defined as formulas. But we also can modify its definition. I will erase the initial inverse equation, and one can easily see that now mu t is an image of the initial distribution when we have here 0, 0, under the mapping x t. So now finally, you see, we have the following system of equations, but system in a sense that it contains continuum equations. We start from any point of the space. We have the relation, the infinitesimal increment of the trajectory of this point can be described in terms of the mass distribution of all systems. We start from some mass distribution and go with the time. And now one can understand that instead of this measure, we can consider, for example, mu 0, which is absolutely continuous with respect to the measure. So we have much more freedom, and now we embed this Helmholtz system in the in such equation where the motion of one particle depends on its position and also on the mass distribution of all other particles. This is the second example is also very well known and also very old. Let me recall you so-called filament equation, which was firstly proposed by Landau and Lipschitz. And this filament equation it was proposed to describe the motion of the curve in the liquid or in the gas. So they tried to describe the evolution of the curve with the time. So they considered closed curve, and in this case, this curve can be obtained as an image of the unit circle. And if we have here natural parameterization by theta, then at the time t position, at the time t, our curve can be described by the x, theta, and t. This is the position of the point of the curve related to the parameter theta at the time t. And the initial initial equation for the motion of the curve was the following. Dx theta dt will be equal to some coefficient k depend on theta and d, and multiply on the dx theta d, which is equal to d theta, and here is vector product d2x theta d multiplied on here is the model of the motion, and it is motivated by the Book law. This came from Book law. This came, so for simplicity, one can suppose that now it is constant. And you see that it is also a equation where the motion, the infinitesimal increment of the trajectory of the point of the curve, which is related to parameter theta, so these derivatives depend at least on the infinitesimal neighborhood of this point on the curve. But let me mention that if the very interesting thing, it occurs that if we suppose that instead of the our curve, we have a lot of vortices from Helmholtz equation, which are placed in the curve very closely one to another. And then we pass to the limit and try to take into account not all what is as in the equation, but only some small neighborhood. Then correctly passing to the limit, one can get this filament equation from a whole system. So one can see another example where we, again, I repeat, have the following phenomena. The motion of one point depends on the other, depends on the distribution of other points. So it looks like that this is a general picture, and one can try to consider equations where the motion of the particle depends not only on their positions but also on the mass distribution of the whole system. And now let me introduce to you the main object of my lectures. It is the following. I will consider the following equation in the finite dimensional space. Now dimension is equal to d, and it is a stochastic differential equation. But in the coefficients, you can see, as usual, the process which we want to obtain. And here, mu t, I will consider autonomous case. All the clauses can be old-fashioned, can be built here without any difficulties. So one can consider non-autonomous case of random coefficients, and so on. But this is only fashion. Let's consider the idea. So t plus stochastic term. I prefer to write stochastic term in slightly more complicated way as usual. So it will be integral v x ut e w dv dt. I will explain what is it and rewrite it in much more familiar form. Initial condition is the following. Here we start from every point of R, and what is mu t? Mu t is a distribution, is the image of the initial distribution, excuse me, under the floor x. So when we, as usual, put here a bracket, then we have to add to this Cauchy problem this relation through which different points interact one with another. So I called, when I introduced this equation, I called it equation with interaction due to this term here. I must say that I proposed this equation after collaboration with Peter Kotelenis, who discussed similar things related to this R exactly as the Markov equations. So what is it? W is with shift. This is a Hauscher measure. Is a random Hauscher measure. On space and time. And it depends on the picture. It can be with the values in RT. Then it is matrix. For then this is just number, and we multiply the vector. And if this measure has independent values with independent values, it means that on the independent sets, non-intersected sets, it has independent values, and as usual, the structure measure is a Lebesgue measure. If it is not, if it looks too complicated, one can substitute this stochastic term as follows. Plus the sum from k equal 1 infinity bk x ut d w t, where this sequence is a sequence of independent linear processes are deregulated. So in such way, we will describe stochastic term in the equation as operation. There are some reasons which we will see further, which leads to the infinite number of the linear spots here, or to this random measure. This is not efficient. We really need such infinite number of the processes. But of course, when considering examples, one can start from the equation interaction just as one. So this is the main object of our consideration. And before to discuss the properties of the solution of such equation, it is reasonable to consider the conditions under which we have the solution, and we have uniqueness of the strong solution to this equation. Of course, the first which we have to discuss is just the usual generalization of familiar conditions for ordinary differential equations, namely Lipschitz condition. In order to assume here Lipschitz conditions on the coefficient, we need to understand in which sense we will have the Lipschitz condition with respect to the argument from the set of measures. So let's have a short excursion to the Wasserstein distance and to functions which have Lipschitz, which are Lipschitz on the space of measures. As we have seen in example with Hermann's equation, the measure mu will be supposed to be finite. So, without any restrictions, I will suppose further that mu belongs to the set of n. This is where n is all probability distributions on R. When I'm saying R or RT, of course I suppose that we consider the Boyle sigma. Now let us define the distance. For two measures mu and nu, I will consider the set Q more mu. This is the set of all measures in the product are given such that new are projections. So we have the following picture. Suppose that here we have distribution mu, here we have distribution mu. So we discuss such measures in the product. Then, if I consider a projection such cylindrical set, then the kappa of this set, let me denote by H, for example, will be equal to mu of D. And the same happens when we make projection there. At least one representative here exists, because it is trivial to see that mu multiplied by mu belong to kappa. But it occurs that Q mu nu can contain much more than one measures, and one can look for the measure which is close to the diagonal. Of course, if one can find such measure on the diagonal, then mu is equal to. Then, more close we can find our distribution to the diagonal in the product from the set. Then, in some sense, mu and nu are more close one to another. From this point, one can introduce the family of the Wasserstein distances. Here, I will denote gamma p. Let me start from gamma 0. Gamma 0 mu is the ink with respect to Q mu of such integral with respect to RG. Here we have more u minus v. 1 and more u minus v. Kappa du dv. Here is gamma 0, and of course we want to have some distances related to the moments. So for p, which is greater or equal than 1, gamma p mu nu is the Q mu nu And here we have the such integral of d naught u minus 3 power kappa du dv, and then 1 over. Of course, now such number is well defined only for measures in U which has p piece moment. So this is a distance not on the whole space mu m, but on the space mp. These are the measures with finite moment of the order p. Here, this is a distance of the whole space. To check that this is a distance, it is interesting exercise. And as a hint, one can say that when you want to check the triangle inequality, you can use the theory of Markov chains. It is interesting to solve it. But it occurs that all this space with these distances becomes to be separate complete space, non-locally. By the way, convergence in the Wasserstein distance of the order 0 is equivalent to the weak convergence of the measures, and convergence in the Wasserstein distance of the order p is equivalent to the weak convergence and boundedness, uniform boundedness of the moments of order. So it is more or less familiar to probabilists, these distances. They have an interesting relationship to transport problem, and I hope to discuss it in our seminar maybe in the end of May. But it also must be mentioned that there is very good application of these distances to our proposals, because it is very easy to estimate distances between the image of the same mesh. Let me show what happened, because we will use this estimation in the future. Suppose that we have measure U0 and have two measure functions f and j, which are taken from articular weights. Then one can define this measure mu as an image of U0 f, and one can define measure u as an image of the same distribution U0 under the matrix. Then one can very easily find a good representative kappa from this set of measures which has mu and mu as the maximums. In different theory, field of random process speed sense, this is a coupling of the measures mu and mu. So how one can define this coupling? Very easy. Let us define the coupling as an image again of the measure U0, but on the under the matrix F and J. So this pair maps Fj. Now F are acted from RD to RD multiplied on RD. So it's very easy to check that this is really representative of this set. And moreover, when we discuss the distance, now, for example, considering distance indexed by 0, gamma 0, then it can be estimated from above by the following: now f of u minus f of v minus j of v u, and here is 1 plus norm of f of u minus j of u, and this gives 0. And you see that when we have the images of the same measure, it is trivial that these images, the distance between these images as between the measures, can be estimated using the estimation of the difference between these two magnitudes. This is a very good property which is widely used when discussing the equations. Now let us came to our coefficients, which we already wrote when considering general form of the equation with interaction. Let me recall this form: dx ut is equal to h x ut dt plus the integral respect to r d x ut mu t p w dp dt. And we also have the initial condition x is equal to u will move to rd, and finally ut is an image of the initial method u0 under the method x. Okay, so let me recall that we want to have generalization of the most well-known, most used statements that when coefficients are Lipschitz, we have a unique solution to this equation. So we want to understand what is the meaning of the Lipschitz condition which is referred to this measure. So I will just consider some examples. Let A x from RD multiplied by M, and RD. So what we need two examples. We need to have examples of such methods which are Lipschitz with respect to the second method. Of course, we understand what it means formally, but to have a good example, let's come back to Helmholtz equation, and we understand that the real example of such coefficient can be following. Let us take some kernel alpha, which act from RD multiplied by RD to RD. Of course, it is measured, and then define age of x mu is equal to integral with respect to RT alpha x mu dv. Why I'm choosing such form of the coefficient? Let me inform you that when we have the discrete measure mu zero, for example, suppose that mu now is just the sum of k equal 1 to n here pk delta dk. So this is as we discussed. Delta function measures the weight 1 concentrated at the point uk, and this is real weight of this point. So the sum of this small pk is equal to 1, they are positive. Then what we will have? Then our a x mu became to be as a sum from k equal 1 to n, and here we have pk h x uk. So you see, this is exactly the form which we have in Helmholtz equation. Instead of this a, we have those orthogonal gradient of numbers. So one can say that such kind of equation, such kind of the coefficient is related to what? To pairwise iteration. And momentarily, when we give such a name to this coefficient, we can get a lot of good examples of the coefficients. It depends on the measure. Just taking into account the interaction between the final sets of our points. So, for example, now a equal a x mu is equal to the integral, and we have here k and a x u1 uk mu du1 mu uk. So this is coefficient related to k plus 1 interaction. By the way, such kind of integrals, when we fix x, seems to be natural generalization of the powers of the measure mu, and one can discuss the polynomials with the measures with such organized from such multiple integrals. And we will see interesting phenomena that despite that our m are not locally compact, when we will discuss Markov processes related to solutions to equation with interaction, it occurs that the generator of this process is sufficient to define on the polynomials. It is interesting thing because the set of polynomials is very thin now in the space of all continuous function on the space of measures. But it will be in the future. Right now we understand what kind of coefficients we want to have. Now let's see when these coefficients satisfy Lipschitz condition. It's easy to understand when we discuss the space related to the space of measures with finite moments. Then nothing new happened. We just have that, for example, let us consider such background. F of v mu d. Then if f is Lipschitz and mu has and then this is a Lipschitz function on the space and E of P. But for M0, we need something else, and it occurs that we have interesting relationship that if F is Lipschitz and bounded, then this coefficient also became to be Lipschitz function on this space. It's also it's a good exercise. So now we understand the example of the Lipschitz coefficients, and you can come back to our equation. And the theorem is expected. I can see the MB, where P is Markov, and equation has the following form: dx ut is equal to hx ut d plus integral g b x ut p excuse me ut p w dt, and we have starting condition u belong to RD and mu t is equal to mu 0 and this mechanics E. Then when A and B are Lipschitz, then we have existence and uniqueness of the solution. This is the theorem, and one can imagine that maybe, as usual, when we have Lipschitz coefficient, to prove this theorem, we will apply the method of iterations. It is true. But I must say that now we will have two steps on every iteration. Why? Because we have here additional coordinate mu. So we define x0 and mu0. Then using mu0 we define x1 and mu1. Then using mu1 we define x2 and mu2, and so and on every step we need to check the distances between obtained flows and obtained meshes. And as I told you, the distances between the flows gives us estimation for the distance between the meshes, because the meshes are the images of the initial measure used. This is the idea. It can be realized, and we know now that our equation of separation has a unique construction. So now let us say some words about the future investigation, because what we want to have we want to consider the limiting behavior. This usual question relative to any stochastic deterministic system which describe some evolution. So maybe some questions which we propose will be about the limit of asymptotics of the infinity for our solutions. And now let me show just very simple example which will give us a flavor of what we can obtain. So this is the known Kuramoto system. This is a system of the harmonic oscillators which are connected one to another. So this is I am writing equation for the angle. We have a point in the circle, and as usual, we measure, we identify the position of the points by this n. This is the point with the number e, and I identify that with n. So this is equation for the angle. It's equal to 1 over n sum j 1 over n sine of phi t minus phi gt. Okay. Dt. So you see that this Kuramoto system is a classical system with the interaction. Because if I define the measure mu t, which is just 1 over n sum from k delta phi k t, then it can be written as integral from sine. We did this several times during my lecture today. And we have exact equation with interaction. Why I am showing you this example? Because it arose in applications and demonstrate interesting behavior. There are no point of attraction. So one cannot say that with the time all the points will be near some fixed point on the surface. There are no such kind of behavior, but it demonstrates interesting behavior. These points more or less concentrate near one point, which is moving. So we have some concentration of the mass, but this mass is moving along the space. So when we consider equation with interaction, we can expect that we will have some asymptotic stability, but we will see that this stability is exactly like in this example. So we will have the phenomenon of mass concentration, but it concentrates near the point which is floating around the space. So, relatively to this, we will have different questions about the methods how to check such kind of phenomena. Also, we will discuss Markov properties which arise as a solution to equation with interaction. Because here we follow more or less easiest way when we study diffusion processes. Yes, one can study diffusion processes by two ways. One way is let us consider continuous Markov process which has some infinitesimal characteristics. This is Kolmogorov. Then let's start to study it, get generator, and see that maybe when we consider some stochastic differential equation, we get the same generator. But one can do this in an opposite way. Let's consider stochastic differential equation, get the solution, take harmonic function for generators, study the recurrence of transition phenomena, and so on. And then say, okay, this is a Markov process which is diffusion. So in this case, we will do this. We consider the stochastic differential equation in this direction. We will define some type of Markov processes, consider its generators, properties, and so on. This is the subject of the my second lecture. Today, that's all second lecture. Maybe there are some questions, please.
Thank you for the interesting talk.
I hope that the next will be much more interesting because it will contain some application. And this is just advertising. After my lectures, Yasmina Georgievich will have 2 lectures devoted to the backward stochastic differential equation and interesting problems with 2 equations with interaction.
And is there any chance to have something like Wasserstein distance for infinite measures?
Yes, we can define something like this artificially. When we just restrict it on the parts of the space and suppose that these measures are locally finite or something, one can try to do this. But after this, we face a lot of troubles related to estimation of this distance. Because when we have only locally finite measures, when we do this mappings, which I showed, this is trivial for such case, but becomes to be non-trivial for measures which are only locally finite. So I think it is possible in the special cases when we have a lot of special conditions.
Thank you.
Okay, if there are no other questions, thank you for your attention and see you on my next lecture. Okay.